Good afternoon, class. Today I'll explain how to find angular momentum. An angular momentum and a conical pendulum, which is what I have just solved a question on. If the conical pendulum is being given and rotated with a constant angular speed of omega, what factors will change in it? The first and the foremost which we need to realize is that angular momentum cannot be calculated unless and until it is specified about which point, or for that matter about what axis it is assumed to be calculated. So we're assuming over here that angular momentum is to be calculated about the point of suspension of thread. So we take thread, that thread is suspended by a point, it goes into forming a conical pendulum, and conical pendulum is rotated with a constant angular speed of omega. What we do next? We are to first calculate what is the torque about point of suspension. Of course, torque due to tension will be zero as tension passes through the point of suspension, but will not be the same of mg about the point. So about the point, mg is producing a torque, and if mg is producing a torque, needless to say, torque is equal to dl by dt. So L dl by dt is equal to torque, and torque is not equal to zero. That lets us come to the conclusion that dl by dt is not equal to zero. So delta L is not equal to zero. L is therefore changing. Now L can change only because of change in magnitude, only because of change in direction, or it can be a club of both. Here what we need to calculate is what is happening to L. Is it changing courtesy both or one of the two? Let us then calculate what is L as per magnitude. Now L is equal to r cross mv. We know for a particle L vector is equal to r cross mv vector. So L magnitude wise is r mod mv mod into the perpendicular distance between r and mv. What we get to see then from here is L is not changing on magnitude front, but when you check on its direction, L, which is equal to r cross mv, you will extend the vector r, and mv is known to you. So r cross mv, when you'll find, of course, should be perpendicular to both. As we know, if we take a leaf out of our vector calculation, we know that the cross product should be perpendicular to both the vectors going into forming it. So r cross mv should be perpendicular to both r and mv. As the conical pendulum is rotating, what is happening to L? L is also changing its direction. See this way. Conical pendulum, L will change the direction to go this way. So what we can say? Magnitude remains same, no doubt about it, but direction will keep on changing. One more misconception that I like to clear off over here is dl by dt. When you write dl by dt, which is equal to torque, and torque we write is equal to r cross f. Please do keep it in mind that this is good till the time we are using a particle system. If you go for a body, then this is to translate to L is equal to I into omega. Now generally we don't find L vector is equal to I into omega. We find L is equal to I into omega being marked over there. Is because if you're talking of L vector, then you will have to ensure that the axis of rotation should divide the body symmetrically. If it divides the body symmetrically, only then we deem fit, or only then we do qualify, let's say, writing L vector is equal to I into omega vector. Else we cannot write L vector is equal to I into omega vector. We'll have to take it component wise, x component, y component, and accordingly we write about the axis of rotation. So L about axis of rotation is equal to moment of inertia about axis of rotation into omega about the axis of rotation. This is what we have. This is a very important point which is being missed in general in class. That's all for the day. I'll keep to this. Fine, let us call it a day. Thank you, class.